This video is the second in a short series on antiderivatives and indefinite integrals, and we're going to start by reviewing the definition of antiderivatives and indefinite integrals. Then we discuss the indefinite integral as a one-parameter family of curves. We learn to use the antiderivative to solve simple differential equations and initial value problems. And finally, we apply the antiderivative to solving an initial value problem in one-dimensional kinematics. In other words, the motion of a particle in one dimension. As a quick reminder, the antiderivative of a function is the thing you differentiate to get that function. More formally, we say that if we're given a function little f of x, then big F of x is the antiderivative of little f of x if its derivative is equal to little f of x. We quickly realized that adding a constant to big F of x gives us another valid antiderivative that still differentiates to the same little f of x, since the derivative of a constant is 0. Next, we showed that big F of x plus c, in other words, some antiderivative of little f plus an arbitrary constant, is the most general antiderivative of little f of x. In other words, every antiderivative has this form. And finally, we introduced a new notation for the most general antiderivative, and that's the indefinite integral. So we have the indefinite integral of little f of x. That means the most general antiderivative, big F of x plus c. So we noticed that the most general antiderivative, or the indefinite integral, is not just a single function, but it's an infinite number of functions based on our infinite number of choices for the parameter c. So we call the most general antiderivative a one-parameter family of curves. To illustrate what this means, we take the example of little f of x equals x squared. We're asked to compute the indefinite integral and then plot several antiderivatives in the family of curves. So we have to start by basically guessing the antiderivative of this little f of x. And we can see that x cubed almost gets it done because the derivative of x cubed is 3x squared. And that's just using the power rule for derivatives. Well, if we put a 1/3 out in front of this thing, that would take care of the factor of 3. So when we differentiate this, we get 1/3 times 3x squared, which is x squared. So our big f of x is 1/3 x cubed, and our most general antiderivative, in other words, the indefinite integral f of x dx, is going to be 1/3 x cubed plus c. So we plug in a bunch of different values of c and fill the plot with this one parameter family of curves. And we can see from the plot that every one of these curves in the family has the same slope at the same values of x, because each of these curves is simply a vertical shift compared to any of the others. Next, the antiderivative can give us the solutions to a certain class of simple ordinary differential equations. Those are also called ODEs, and initial value problems. Those are called IVPs. So just some quick definitions here. An ordinary differential equation is just an equation that has derivatives in it. And we're restricting ourselves to the first order case, meaning we just have a first derivative, no second or higher order derivatives. Now, the general solution of a differential equation is the most general function satisfying the equation. And I need to point out here, the solution of a differential equation is a function. It's not a number like you're used to for algebraic equations. It's a function that obeys the equation. So a particular solution to an ordinary differential equation is a solution that passes through a given point. That point is called the initial value. And an ordinary differential equation together with an initial value is called an initial value problem, or IVP. So when we're given an initial value problem, the goal is to find the particular solution that satisfies the original differential equation and also passes through the specified point. In this example, we're given the first order ODE, f prime of x is equal to x. And again, the solution of this equation is a function, f of x, that makes the equation true. First, we're going to go after the general solution to this, which will come with the flexibility of an arbitrary constant. And then we're going to apply the initial value f of 0 equals 0.5 to nail down the particular solution. So to find the general solution, again, we're basically just guessing here, or if you like, we're using the power rule backwards. I have the first derivative of a function is equal to x. So I just have to figure out what function do I differentiate to get x. And it's basically x squared, but we have to adjust for a factor of 2 out in front. If I differentiate 1/2 x squared, the power rule brings down a factor of 2 out in front. It cancels the 1/2. And I get f prime of x is equal to x. So this is the meat of the general solution, but I need to put in an arbitrary constant of plus c, because again, there are infinitely many functions that differentiate to x. They all just have different additive constants added to the 1/2 x squared part. Now we can visualize this general solution as a family of curves. Now in the plot, we're showing the original curve for f prime of x. That's equal to x, so that's just a line. And now we overlay this family of curves for a bunch of different values of c in our general solution. Next, we want the particular solution of this differential equation corresponding to the initial value f of 0 is equal to 0.5. So all we do is take the general solution and say, okay, f is equal to 0.5 when x is equal to 0. We'll just go ahead and plug those in. 0.5 is equal to 1/2 times 0 squared, and of course that term vanishes, plus c. And immediately we figure out what c is. C is 0.5 in this case. So to find the particular solution of the equation, we just take the 0.5 and plug back into the general solution. And we see in the picture that enforcing the initial value selects one particular curve out of the one parameter family is the curve passing through that point given by the initial value. Finally, we apply the idea of an initial value problem to a classic sort of question from introductory physics and calculus. We're given the velocity of a particle as a function of time. We're given the position of the particle at one particular moment in time, and we want to find the position as a function of time, and then the displacement, in other words, the change in position for a given time interval. So we have the velocity function 3 minus 2t squared for v of t, and we have an initial position of 1.5 meters when t is equal to 1 second. And we're noting here the units of velocity are meters per second. So we're doing everything with distance units of meters and time units of seconds. And the key to the problem is to remember that the velocity is the time derivative of the position function. And if we plug in that velocity function, we realize we're looking at a first order ordinary differential equation. I have x prime of t is equal to 3 minus 2t squared. So the general solution is found by basically just guessing the antiderivative of this function to get x of t, the position as a function of time, the thing you differentiate to get x prime of t. And we go term by term here. The antiderivative of 3 is 3t because that's what I differentiate to get a 3. What about the t squared term? I know the t squared part has an antiderivative of 1/3 t cubed, and the constant in front is a spectator, so I end up with negative 2/3 t cubed. And as a general solution, it's got to come with an arbitrary constant. The most general antiderivative that differentiates to the given velocity function is 3t minus 2/3 t cubed plus an arbitrary constant, c. Now we're still not done answering part A. To get the position as a function of time, we need the particular solution of this. In other words, we need to nail down the value of c. And this time, our initial value happens when t is equal to 1. And when t is equal to 1, x is equal to 1.5. So we plug in 1.5 for the position when t is equal to 1. Subbing in t equals 1. The first term is 3 times 1. The second term is 2/3 times 1 cubed. And I have a plus c. And we'll go ahead and clean things up and do it in exact form here. Because I know I'm going to have to deal with some fractions, I'm going to write 1.5 as 3/2. And then I have a 3 times 1, which is 3, minus 2/3 times 1 cubed, which is minus 2/3, plus c. And we can isolate c and then do all the fraction addition and subtraction. So c is found by taking 3/2 minus 3 plus a 2/3. And the common denominator here is 6. So multiplying that first fraction by 3 over 3, I get 9 over 6. Multiply the 3 by 6 over 6, I get negative 18 over 6. And finally multiply the 2/3 by 2 over 2, and I get 4/6. Now we can do the subtraction and the addition. I get 9 minus 18, which is negative 9, plus 4, which is negative 5. So I get negative 5 over 6. Now that I have the value of c, I plug back into the general solution. I get my particular solution, which describes the position as a function of time for this particle. Now in part B, we're asked for the displacement, and we're told this is the change in position from t equals 1 second to t equals 3 seconds. So the displacement is just the position evaluated at the final moment in time, in other words, x of 3, minus the position at the initial moment in time, x of 1. In physics courses, this is generally given the symbol delta x. So all we have to do is sub in t equals 3, sub in t equals 1, and do the subtraction. So subbing in t equals 3, I get 3 times 3 minus 2/3 times 3 cubed minus 5/6. All right, there's the position when t is equal to 3. I have to subtract from this the position at t equals 1. And there's a nice shortcut available here because we already know the position at t equals 1. We figured out what c is based on applying the initial value, x equals 1.5 when t is equal to 1. So if we did everything correct, the position at t equals 1 should be 1.5. So for our first term, we have a 3 times 3, which is 9. For our second term, a negative 2 times 9, or negative 18. And then we have a negative 5/6, and again, we can write 1.5 as 3/2. So combining the whole numbers, we have negative 9, And then we'll go ahead and combine the fractions right now. The common denominator is 6, so I multiply the second one by 3 over 3. I get negative 5 minus 9, or negative 14 over 6. Expressing the negative 9 with a denominator of 6, that's negative 54 over 6. And I have a minus 14 over 6. This gives me negative 68 over 6, which reduces to negative 34 thirds meters. Now in a calculus class, you're probably going to leave your answer that way. In a physics class, you're going to round it off to a few decimals, and that rounds to about negative 11.3 meters. And we're done. If you enjoyed this video, or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.